Alright, now let's move on to the SQL strategy, and I'll also tell you the reason why I'm calling it a 1D trap. Okay, to write a query, we first have to speak the database's language. Our user gives us a radius in kilometers, and but our databases stores the locations in coordinates. So how do we bridge that gap? On our planet, 1 degree of latitude is approximately equals to 111 kilometers. So if we want to find a 1 kilometer radius, we simply divide 1 by 111, which gives us approximately 0.01 latitude. This is our magic number now. To create a search area around our user at 40.71 and minus 74.00, these are basically our user coordinates. So we need to create a search box, or we call it as a bounding box. We basically add 0.01, which was our magic number, to the latitude as well as longitude to get our lower bounds and upper bounds. So if you see over here, if we subtract 0.01 from 40.71, we get 40.70, and if we add 0.01, we get 40.72. So similar thing which we do it for longitude as well, we get this minus 74.01 and minus 73.99. So when we start writing the query, we have this particular query where we have select name from the businesses, where latitude is between the particular box and longitude is also between that box. So once we have this kind of query, this on the surface, this is perfectly logical. We are asking the database to filter two columns at once. But in world of high level system design, this is where we hit a massive bottleneck. And here is what how actually our database is going to look at it. So when we fire this particular query, we see that the Starbucks uh, is the row which gets filtered out. But with the Starbucks row, we also get this random named restaurants row as well as uh, with that filtered, which also gets filtered out basically. But if you see, it is not in the longitude range. That means the first our database would have actually filtered out all the latitudes which are in this particular range, and after that we are again filtering out the longitudes. So if you see, this is a strict order of n complexity problem where we have to scan the whole database uh, and then get all the businesses which are within the search radius given by. Okay, so let's summarize the strategy we just walked through. We have our user at say 40.71 and minus 74.00. To find the businesses within a 1 kilometer radius, we applied a magic number of 0.01 to create a bounding box. We then fired off our SQL query, which was select name from businesses, where lat is between this particular two numbers and long is between this particular two numbers. On paper, this query looked clean, logical, but in production, this is where wheels fall off. Here, the under the hood reality of how this query works is based on how our database is just a one-dimensional thinker. First, it checks the latitude range, which is over here, and then it uses the index to find every single row between 40.70 and 40.72. So in our example, Starbucks and random was considered out of the filter which we had, and after that the longitude was also compared. So if you see over here, for every single one of those filtered rows, the database must perform a secondary check for longitude range also. This is a bottleneck. The database is doing double the work because it cannot filter both dimensions simultaneously. Now, if we also look at our back of the envelope calculations, we estimated that our system needs to handle 200 million businesses. So in a databases of that size, a latitude strip of 0.02 degrees could easily contain 500k to 1 million records. And this will surely be a very slow query, I would say. And this leads to a massive spike in CPU usage and disk IO as well. Our latency will skyrocket from milliseconds to second, and the system will eventually time out. This is an order of n complexity in world that requires login speed. Now, to tackle the problem of 2D coordinates, we have Geohash. So, this hash works by reducing the 2D longitude and latitude data into 1D string of letters and digits. It works on recursively dividing the world into smaller and smaller grids with each additional bit, so that our planet is divided into four quadrants along with prime meridian and equator. So how it works is we have an algorithm for it where we have defined the ranges for latitude and longitude. For latitude it is minus 90 to 90. For longitude it is minus 180 to 80. Minus 180 to 180. After that we do a binary search partition for each coordinate, and based on the search space, if it is greater than mid it will be a bit 1, else it will be a bit 0. We repeat this process till 15 times, because say if we want to have a 6 byte precision for geohash, we would do it for 15 times each for latitude as well as longitude. In this way we'll have those 30 bits. After the interleaving of that 30 bits, we convert the whole thing into a base 62 encoding where we group by 5s, and then we finally have the geohash of that particular longitude and latitude. Yeah, so if you would have not understood the algorithm, which is perfectly fine because I have got the example for the same coordinates, that is 40.71 comma minus 74.00, we will calculate the geo hash for this particular coordinate. So we will be having at the end, once we complete this algorithm for this coordinates, we would be able to generate a hash for this two coordinate. And the algorithm which I mentioned just before this is used to get that hash. So initially, as I told you, that we will be having latitude calculation as well as longitude calculation. So our latitude lies from minus 90 to 90, whereas longitude lies from minus 180 to 180. So initially what we do is, as our latitude lies from minus 90 to 90, the midpoint is 0. And if the coordinate is greater than the midpoint, we will simply have bit as 1. Okay, after that, once if the bit is 1, then we will actually reduce the search space, which now it becomes from midpoint to the higher bound, which is 90. So it will become 0 to 90. Again we calculate the midpoint, which is going to be 45. We'll check if 45 is lesser than 40.71, which is not, so that's why we would say bit is equals to 0. So we just have to remember that if midpoint is greater than the coordinate, then the bit would be 0, otherwise bit would be 1. So similarly we do it 15 times for latitude as well as longitude. So we get, at the end we get a 15-bit array for both latitude as well as longitude. So if you see over here, we have 10111 for latitude, and 01001 is the bits array for longitude. Once we are done with these arrays, once we are done with the calculation of this particular bit arrays, we interleave this both strings. So we can call it array, we can call it strings, whatever we want to. So once we have got the strings, we interleave the strings. Now what do we mean by interleave is that we take one string of longitude and one string of latitude respectively. So if you see over here, 0 is taken first, then we take one character from the latitude string, which is 1. So we have taken 1 over here. Again we go with the longitude's second character, which is 1 over here, and 0 from latitude. So if you see, we have 1 0. So similarly we just interleave both the strings, and then once we have interleaved both the strings, we get a 30-bit string at the end. Once we have the 30-bit string, what we do is we group it in fives, because base 62 obviously has 5 bits because it is 62 base 62 encoding. Once we have got the 30-bit string, we encode it in base 62. So first of all we convert those, we group those into 5 5 groups, and then we convert into decimals. So this particular 01100 is basically 12 in decimals, and 10111 is 23 in decimals. We convert that into base 62. 12 is basically D in base 62. 23 is represented by R in base 62. Once we are done with all these things, so if you see, our final geohash would be dr5rmw for the coordinates 40.71 comma minus 74.00. So now if you see, our coordinates which were two dimensional are converted into a string, and this is what the magic which goes behind this geohash algorithm. Just 2 points to note about Geohash is that Geo has 12 precision levels. So precision factor actually determines the size of the grid. So here, if we have, let's say, a 6 sized hash, it would be more accurate than 4 sized hash. So if I just talk about the rough figures, if we have 0.5 kilometer radius, it is roughly equal to 6 geohash length as well. And if we talk about 20-kilometer radius, it will be 4 geohash length. So basically, the higher or the longer the length of the geohash string, the accurate the grid size is. So the deeper we move into any kind of map or any kind of geographical data, the higher or the longer the length of the geohash is. Now, before wrapping up this whole geohash topic, I would actually like to explain you guys about one of the famous DSA question, which is related to what we just learnt about. That is interleaving strings, which is on lead code and is a very good question. And in the lead code version of it, we are given two strings and asked if the third string can be formed by weaving them together while maintaining the original order of characters. It is labeled as hard problem because it usually requires dynamic programming to solve for all edge cases. But if we look at how we just use it in our proximity service, we didn't just interleave the strings for fun. Our S1 or the string S1, which will be given in the lead code, is the latitude sequence, and S2 would be a longitude sequence. The resulting S3, the interleaved string, becomes our geohash. So let's jump on to the lead code question, what we have got, and maybe I'll explain you this thing once again. Let's start with the problem, which is on lead code interleaving string. So here also, if you see, we have been given two strings S and T, which I mentioned earlier, where we just need to see if S3, which is there given to us, is a interleaved string of S1 and S2 or not. We just have to return true or false at the end. So if you see over here, and the thing which we talked about in our geohash problem was we were interleaving the strings or weaving the strings one by one. Let's say if this was the longitude string and this was the latitude string, we were taking one by one characters. But in this problems, we can have more than one characters also being interleaved from the both strings. So here we just have to return true or false. So, and also if you see over here, the standard string lengths are being given as 200, and the S3 is obviously 200 because at max both can be 100. So interleaved string would be 200 length. So we have been given this problem, and by seeing the constraints only, you would get to know that this is something where we have to try the possibilities and get the answer. So the thing which we would actually use over here is dynamic programming, and the way I think at it is mostly with respect to solving this string problems into 1D one based indexing. So what I generally do is I extract the lengths of the particular strings initially only. So that will be, so I'll call it as n1. It will be s1 dot length. I'll quickly calculate the s2's length as well. I'll also let you know what my intuition is behind this kind of problems. So int n3 is equals to s3 dot length. So now that we have all three links length, what I would do actually in my case over here is, uh, let's say we have s1 and s2 over here, right? We compare the last characters, which is c and a, with the s3's last character. So if you see over here, obviously one has to match. So in this case, c, either if c matches with the s3's last character, which is also a C, then we would actually tell the recursion to solve for this particular string till this length and s2 as like whole length, because in recursion what we generally do is we solve a bit of the problem and the rest problem we give it to the recursion itself to solve it by its own and return us the answer. I'll explain you as in we write the code, because the code will be quite intuitive, because I'm writing a recursive code for this first, and then we'll quickly memoize it and we'll see if the solution is working or not. So initially I will just have a function, a recursive function, where which would take the input as the lengths or maybe the last indices of the all three strings. So let's say I have this, I have s1, I have s2, I have s3 as well. So I've got this function which will basically return my answer. So this will be a bool f. I will just have int I, int j, int k. Okay, and I will pass it by reference all the strings so that we are good with the memory as well. S3, yeah. So now that we have given the problem, we are given the recursive function which I'll be solving. So initially we assume the base case first. So in the base case, we generally think of the most basic case which might happen with this problem, where let's say all the three strings have the length as 0. So if the lengths are 0, then obviously our I would be 0 and j would also be 0 and the k also would be 0. So in such cases, obviously we have to return true, because empty strings will always be interleaved. So I just return a true in such case, and this becomes my base case for this particular recursive function which I've written. Okay, now let's write the conditions. So let's say if I have, because it's one base indexing, right? I will be having this check where, and firstly I'll be checking if all of my three strings indices are greater than 1. So this is how I check it. So once I have this check, now I'll be checking because I'll be going from bottom, I mean the last of the both strings, and comparing with S3. So I would have two cases. Either my both, let's say S1 would have, S1's last character is C anyways. S2's last character, if it would have been C, then we would have been in dilemma that which one to consider. S1 should be considered or S2 should be considered for interleaving. So in that case, we would actually, return, uh, we'll try to recurse on both the strings. By that, what I mean is when I write the code, you will get it better. Is, let's say I have a S1 of, let's say I minus 1, I would say, which is equals to S3's k minus 1, which is the last character of S3, and S2's, which is j minus 1, is also equals to S3 k minus 1. So if this condition is true, then I basically what I would do is I would try both the possibilities. I would say that return where f So what I would do is, let's say I will try for the first string and the third string. So basically S1 and S3 I'll be trying, because C matches in the last characters of both the strings. So I would say that, reduce I minus 1, which will be like, I'll ask recursion to, solve for the strings length, which is one lesser than what we have right now. So immediately we would pass on I minus 1. We would pass j as it is, because we are not decreasing the length of s2, because we are thinking that we'll try it in the second case. So here it would be I minus 1 comma j comma, we would also have k minus 1 over here, and then we'll be passing s1, s2, and s3. So this is my recursive function. We would try the other possibility as well, where we would not consider, still if we here, because I'm saying that here also we would have a C, right? So if both the cases have C, still we would not consider S1, because in this condition we are already considering it. But in the second condition we would consider S2 and S3 as interleaved string, and then that's why we would pass I as it is, but we would pass j minus 1 and k minus 1 here. So whichever actually returns true will actually return the whole parent as true. Okay, so everything will come out as here true here. Yeah. So we have got this particular case now. Now let's say only now the other two cases would be where only one of the characters only matches with S3. Okay. So here I would say that I am just checking for I and K, and obviously this wouldn't be here. I would just say that, return for this thing. If you are able to return a true, you return true. If you are returning a false, that is also fine to us. So similarly, what I would do over here is I'll just copy this once again. Now the next time, which is over here. Now if you see, actually the existing case which is given, C and C matches. So what we say that you just solve for this part of the S1 now. That's what I have given over here, I minus 1 and k minus 1. Okay, and j is as it is from here. So still, so this is how we reduce the length of the strings if it matches. So similarly, now we would have the second condition where it is j minus 1 and k minus 1, where if the second string, matches with the second string's character, matches with the third strings character, which is, so here we would have this case where s2's character matches with the s3's character. So we've got this. Okay, we have actually solved this part, and at the end, if nothing matches, then we would say it is a false. Okay, so I have written this recursive function. I know we need to memorize this as well, but we'll just see if the test cases are running fine or not. Let me just make it single t. I'll just see if test cases are running fine. I'll just quickly memorize it if everything runs well. Okay, so this looks fine to me. At the end, I would just memorize this particular thing by having a 3D vector. Okay, and I will be passing this. I just memorize it by just passing the DP array into it, and uh, one second. So I have this, and now I've got just the final check. I'll just copy the snippet which I already have. So if you see, I have just memoized this particular part. I'm just checking if that thing is present in the cache, just using the cache now here, just saving. This is the saving of the cache, and this is the usage of the cache. I'll try to run this now. We'll see if this works. And yes, I think it's accepting. We'll just submit the solution. We'll see if this interleaving works or not. Yeah, so if you see, this solution has been accepted. So now let's visualize this geohash thing, whatever we have learned. So I'll just explain you how this abstract math of bits and grids is visible in the visualizer. So here, as we have done the all whiteboard things, let's see how the things work in action. This is the Geohash Explorer, and it's the best way to visualize how we have partitioned the world. So if you see over here, the map is divided into large rectangles, each labeled with a character D, 9 or F or whatever you are able to see on the screen. So if you remember, we had that particular Starbucks business location, right, which had the coordinate as minus 40.71 comma 40.7 comma minus 74, which we took the geohash, which was D. So when I write D over here, right, it immediately focuses on the D block. And then if I like start writing the hash which we calculated, it will try to zoom in. So once I write R, which was the calculated hash, it will again zoom in into the R part of that particular box. So if you see, we are moving towards our location or the coordinates. So again, the next character was 5. So immediately we moved on to the 5. And now in this 5 block, if you see, our next geohash was R. So if you see, again we are moving towards the New York location. So as in, when we extend this geo hash, as I told you, there are 12 precision levels. So if you reach till like 12 characters of a geo hash, you will be able to exactly pinpoint the location which you are referring for. So if you see over here, whatever locations are there which are nearby to this particular drfr would have the same prefix. So in SQL, essentially, when you were writing initially, where you're comparing the latitude between this particular two numbers, basically, which you used, and for longitude also you were comparing between the two numbers, and we essentially thought that it was order of n complexity problem, which we then reduced that particular 2D dimensions into one dimension by converting that into a geohash. Now, whenever we write a SQL query for the nearby locations, we would just write a select business from uh, the geohash, and we will use the like query for that, so that all the strings which have the start as dr5r would, all the businesses which have the same geohash would return to us. And if you see over here, if we zoom in, so if you see all the locations which are nearby, because all of them would have the same prefix, the geohash for this particular part would be dr5rb. For this it would be dr5rc. So essentially these two locations are nearby locations. So this is how actually geohash work. But there is some problem also. These geohashes are not very perfect. So there, if you see over here, if you carefully see over here, uh, we have a bit of problem with the boundaries. So if you see over here, uh, here if you see the boundary of this particular hash, let's say dr5r, right, if I just remove r, we are essentially here. So basically, even if these two particular locations are very near, if you see my cursor over here and here, but both belong to different hashes, and this is what makes a problem with geohashes. But how intelligent engineers solve this problem is by taking the nearest neighbors out of it. So first of all, what we do is, whenever we are given any hash, let's say this is dr5, so basically dr5 represents this block. What we do is we calculate the neighbors of this particular block, that would be 6 7 kh 4. We calculate the 8 nearest neighbor. So if you see whatever the neighbor it would be here, we'll just calculate them as well and take them into consideration also when we are calculating the nearby locations, so that we don't miss out because of the boundary conditions. So if you see, I'll just explain you how we will go inside. So we had the hashes dr5r, and then after that, if you remember, we had mw. So if you see how precisely, if we go inside, we are able to locate a particular coordinate or location very nicely. So if you zoom out, if you see, this is the place we were actually referring to. And if you see, we can still go till the sixth seventh level over here as well. So we can, as I told already, that we can go till 12 precision level. So basically this visualizers are very useful for us to understand how things works in terms of geohash. So you guys can also use this visualizer tool to understand how geohashes work. You can also try to see if how we can actually solve the boundary problem. As I told you that the boundary problem can be easily solved by taking the eight nearest neighbors, or this the nearest neighbors for this particular block. If I just zoom in, right, if I continuously keep on zooming, because our geohash is a seven length geohash. So basically, if you see, if you want to just take any, let's say for this p, then you would just take the eight boundary hashes also into the consideration, and you will see the nearest locations for this based on the whatever we have the radius given by the users. So I hope this visualization was helpful for the viewers, so that they can understand how basically the geo hashes work, and how they help us in calculating the k nearest neighbors.
Yeah, so let's discuss the final flow now, as we have completed the geohash topic, where we have seen how geohash is helping us improve the time complexity of the query, where we have now gone from order of n to order of log n, because most of the modern DBs use B trees for string indexes, and for the queries like where geohash is like, and where we have the regular expression for it, this can be achieved in order of log n or order of 1 times. So just to have a final flow where what user does and how the system would work, here are my 4 to 5 points which I have written over here, just to summarize what we are going to do. So initially, let's say there is a user who comes to Yelp, and he finds he wants to find a restaurant within 500 meters. So basically the user would send us, we would get actually his location, the latitude and longitude. Let's say I've taken some sample latitude and longitude, then the load balancer forwards the request to the nearby service which we had, which we have also shown it in our uh, high level diagram, where this is the nearby service. We also have a business service that is for updation related to any client, any business related data. Basically this is for business users, business owners I would say, and this is for the normal users who are going to use our application. Okay, so once we are done with that, then we then based on the user location and the radius info, the nearby service finds the geohash length that matches the search. For example, for 500-meter precision, because he is asking for 500-meter, that means we will need a geohash length of 6 over here, because as I told you, if we increase the length of geohash, it becomes more precise, as we have also seen in the visualization portal, right, where we just saw that we as soon as we increase uh, the length of the geohash, we were able to deep dive into the geographic map which we saw, right? Then after that, the nearby service will also calculate the nearby geohashes also. This I told you because we would be having the boundary problem, right? So based on the boundary problem, we also find the neighboring 8 geohashes also. So at then finally we would have 8 plus 1, 9 geohashes, for which we will be finding the corresponding business IDs which are near to them. Okay, so this will be our first geohash, and the neighboring 8 geohashes actually will be also added into the list. So for every geohash we'll be running this particular query, we'll be getting the businesses, and all the businesses which are gathered using all these geohashes will be returned to the users.